Everyone to the second lecture of 577. Before we start, just want to let everyone know we're recording this time, so if you don't want to possibly get caught in the recording, which includes audio, you might want to sit farther back and not ask questions, but if you don't care, stay up here and ask questions. So a few administrative things. I made a more detailed syllabus and threw it on Canvas. So that should have every course policy I could think of, which was a lot more than expected. One in particular you probably will like is the I don't know policy, which says on any homework or exam, if you just write I don't know, you get an instant 25% on that problem. This is to discourage you from just making up stuff that makes it harder for us to grade. So that's one thing you probably want to be aware of. There's other things like the collaboration policy. You can now have groups of up to 6 people. Obviously, this is so the TA doesn't have to grade as much stuff. But for the problem-solving journal, everyone has to submit an individual file still. But we might just scrap the problem-solving thing entirely. We'll see how it goes. We also got rid of quizzes. This is just because it's an 8-week course, so quizzes just were pointless, so they're gone now. So those are the highlights. You can see everything else on the Canvas syllabus PDF. We're also going to submit homeworks through Gradescope. You should have all been automatically added, but if you weren't, you can register using the code that's in the syllabus. So hopefully everything in the syllabus. If you have any questions, just let me know after class, whenever. So anything about all those administrative stuff before we start? Okay, so lectures, like I said, are going to be recorded from now on, and they'll be linked to on Canvas. There's also going to be additional videos uploaded to Canvas. I haven't decided yet if I'm going to link them to YouTube or just directly import them. If you have preferences, let me know. But otherwise, we'll get started on Recursion. Also, homework 1 was released. It's due Thursday. So homeworks are going to be due every Thursday at midnight. I picked Thursday because then you have office hours Monday, Tuesday, Wednesday, Thursday. So I hope you'll have plenty of time to get help throughout the week. And then, they're released on Friday. So if you want, you can look at the problems. Don't work on them during the weekend, but you can look at them and then they'll be solved in the back of your mind automatically. So I'm hoping you can still enjoy your weekend using this method. And yes.
Thursday midnight is on Friday morning or Thursday morning?
Thursday at 11:59 p.m. Good question. That's also listed on the Gradescope PDF too. It gives you a countdown of when it's going to be due, which is really terrifying, but I think it's useful too. So yeah, also Raul's office hours are going to be Tuesday, Thursday. I don't know what time Tuesday, Thursday, but they'll be Tuesday, Thursday. Probably after 3 p.m. in case people have internships and stuff. But just, so you're aware. And he'll be providing more information about the room and stuff on Piazza today, hopefully today. Any other questions? Cool. So, we're going to learn everything there is to learn about recursion today. We're going to go through the entirety of Chapter 1, Recursion and Induction, from Jeff's notes. We're going to skip selection. I'm going to make a video about selection just because it's a little more complicated. I don't think it would really benefit from interaction. But otherwise, we're going to pretty much go through all of this today, and then we're going to work on backtracking on Wednesday. The homework has nothing on backtracking. In general, you can assume the Monday lectures included in the homeworks, but not the Wednesday ones. Okay. All right. So recursion. So we talked a bit about recursion last time, but let me give you the highlight of what recursion is. If you remember what a reduction is, that's just the simple idea of using one problem to solve another. Not super complicated. But what's cool here is the particular kind of reduction you're doing is you're reducing the problem to the same problem, just a smaller one. So the general schematic here is if you can solve your problem directly, solve it directly. So that's the first step. If you can solve it directly, do so. Otherwise, you can break it down into other instances of the same problem, but they have to be smaller. If they're not smaller, you'll loop infinitely. So in other words, the recursion fairy can only handle instances of your problem of size at most n-1. She can't solve the full problem for you, but she can solve up to n-1, which includes n divided by 2, n over 3, whatever. Anything up to n over 2. So the recursion fairy can handle up to n-1 size. Okay? So that's the schematic, and if you remember last time, I encouraged you to think literally as you're handing the problem, the smaller problem, off to someone else, and they're solving it for you. Don't unroll the recursion, just have faith in the recursion fairy. In the Tower of Hanoi example, remember it's monks who are doing this process, and the idea is, well, you're giving the n-1 top disk problem to the junior monks, and if you didn't really trust the junior monks to do that, you wouldn't have hired them. Like, what's the point of hiring them if you're not going to trust them and you're going to do it yourself? So don't enroll, never enroll. Okay, so this is the schematic, and the first thing we are going to try this on is pancakes. You're probably thinking, well, what do you mean? Okay, so here's the pancake sorting problem. It's this really neat problem that no one ever talks about, but I think it's wonderful. You can think of literally having a stack of pancakes. And each pancake, of course, is a different size. They're not all perfect. And your goal is you have a spatula, just like SpongeBob has, and you're going to stick the spatula under a substack. So maybe you stick it under here, and then you can flip that substack. And there's the flip. So this is just like physically in real life. You know, you put a spatula under a stack of pancakes, you flip it. It's just going to flip. Now, what's your goal in this problem? Your goal is to keep flipping until the entire stack is sorted with the biggest pancake on the bottom. So you want to sort the pancakes so that the smaller pancakes are on top of the larger ones. So you basically want to make it look like a Tower of Hanoi, but they're pancakes. So any questions about the problem setup? I hope it's kind of clear because you just visualize, you know, if you've ever made pancakes before. Okay? So now we want to solve this problem. So if we want to do this recursively, we want to do some amount of work ourselves, and then we want to delegate the rest of the work to the recursion fairy. So what's one useful thing we could do here to help with the problem? How could we make the problem simpler? Any ideas? Yes.
Can we break it down to having the almost completed step upside down over the last pancake?
Yes. So I'll slightly simplify that idea. So we always want to look at the extremes on most problems. So here, what are the extremes? It's the smallest pancake and the biggest one. The idea here is we want to get the biggest pancake out of the way. So let's get the biggest pancake. Out of the way. So since we're sorting the stack, the biggest pancake needs to go to the bottom. So step one is how to get it to the bottom. Suggestions? Yes. Yep, that's exactly right. So what we're going to do, basically the opposite of what the picture's showing. So let's say this is the biggest pancake. It looks like it could be. We're going to put the spatula under it and flip the stack. So now it's on top. So now that the biggest pancake's on top, we can flip the whole stack. And now if we flip the whole stack, the biggest is on the bottom, right? So the answer is flip under the biggest. I'll just call that B. Then flip whole stack. Cool. So after this, so what's the result? We have the biggest pancake, and then we have some substack of size n-1. Okay. Cool. So we have a substack of size n-1. What can we do with that? Sounds complicated. Yes, so what's another way to say that? What's another way to say that? Yes, we are going to ask the recursion fairy to do it, right? So this is the same problem, right? We want to sort those n-1 pancakes. Now that the bottom one, the biggest one's at the bottom, we can essentially ignore it. We can just never flip the entire stack again. We only flip within that inner stack. So this is essentially the same exact problem, just of size n-1. And so we can just ask the recursion fairy to do the rest. To sort top n-1 pancakes. And then we're done. That's it. We don't have to worry about how she does it. We know she can do it. You have to have faith in her. In other words, the induction hypothesis guarantees we correctly sort those n-1 pancakes. Okay. Any questions on the algorithm? As long as you're trusting the recursion fairy, I hope that makes sense.
So, for like assignments, for example, like see the answer for example, if this was question for the homework, we had to submit an answer.
Mm-hmm.
What kind of form would write this?
So the question is, for if this was a homework problem, how would you actually submit this? The answer is, well, this is only the first part, so let me wait till we finish the problem. But fair concern. So the next thing in any recursive algorithm, so we have an algorithm, that's great, but how do we prove it's correct? Using induction. So let's prove correctness. So we're going to use induction. Now, technically, I've glossed over the base case here, and I've done this intentionally. Like I said last time, you always want to solve the recursive case first, and then whatever breaks down in your algorithm, that becomes your base case. So in this problem, the base case is similar to Tower of Hanoi. What's the assumption? The assumption we've made is there exists a biggest pancake. So if there is no biggest pancake, how do we sort it? Well, if there's no biggest pancake, it's no pancakes. So the base case if no biggest pancake, then no pancakes at all. We can sort no pancakes by doing nothing. Okay? I'm guessing you can all believe we can sort no pancakes by doing nothing. So that's the base case. Should be basically an afterthought, but you do need to specify it. So now when we prove this algorithm correct by induction, there's two cases. So this is the base case. Does our algorithm correctly sort no pancakes by doing nothing? Yes. Okay, so then we're in the inductive case. So in this case, we know just by definition of flips we are correctly moving to the bottom. This is by definition of the flipping process. And then the induction hypothesis implies top n minus 1. So we have a sorted stack, and then the biggest, by definition, that's fully sorted. So a sorted top stack plus the biggest is a sorted stack. And that's the full proof. So basically the proof is just how we came up with the algorithm. And like I said last time, if you kind of think about these two things in parallel, while you're making the algorithm, you're thinking recursively, you're going to get your proof of correctness automatically for free. So all we've done is said exactly how we came up with the algorithm. That's basically it. And this might look very informal, but this is a formal proof. We've used all the definitions of the problem. We've used induction correctly. This is mathematically rigorous, even though it feels like it might be obvious. So any questions on this? Yes? So good question. This is actually kind of answered in the homework. So if you look at the homework policies in the homework, it says you can describe algorithms however you want. You can make a bulleted list if that makes the most sense, if that's conveying the ideas the best. You can make it formal pseudocode. Really depends. You need to think about if I'm trying to convince someone or if I'm telling somebody how to implement this in code, am I leaving out any details that might be important? So that's what you want to think about. And you'll get some experience with the right level of detail by looking through the examples. Yeah?
Can I make a drawing that is sufficiently explanatory?
Drawings are useful and helpful, but it cannot be your only answer. I highly encourage using drawings. Any question on the proof, specifically? Yes?
Sorry, can you go back to the graph?
This?
Yeah, I was kind of confused, like, since, like, you said it's similar to, like, the problem we did, like, basically, like, the annoying.
Mm-hmm.
So in this case, we can just, like, stick it through, use the patch node to stick it through the middle and then
Yep. Exactly. So it's literally just like, this quite literally is a physical real-world problem that we've just described in math. This algorithm is something you could implement right now if I had pancakes here. There's no conversion you have to do because it's a mathematical algorithm. So we've described the problem. We've described an algorithm to solve it. We have a proof of correctness. So the last thing we need to do is analyze the algorithm. So we usually care about running time. Here we're going to care about number of flips. So how many flips do we need? So let's call that T of n. So if T of n is the number of flips for n pancakes, can we get an idea of what T of n will look like? So think about this in the worst case. So in the worst case, how many flips do we need to get the biggest pancake on the bottom? 2. So T of n is 2. This is get B on the bottom. Then how many flips do we need to do the rest of the process? That sounds correct, but I want to call that T of n minus 1. So it's however many flips we need to sort the rest of the pancakes. Okay, so we can solve this in various ways. I recommend the recursion tree method that we're going to talk about in a bit, but let's ignore that method for now, and I'm going to tell you the answer is 2 times n minus 1. So roughly, we're using 2 flips per pancake. Yes?
For the last pancake, the smallest one, are we counting the flips for that one too?
So, like I said, this is kind of a worst case thing. This is just an upper bound. So if you wanted to exactly calculate the best number of pancakes, it's going to depend on the specific problem, because sometimes maybe the biggest is already on the bottom. Sometimes, there's clever things you can do in the middle to save time in the future. But if we just were very worst case, in the very worst case, we're doing 2 flips for every pancake. Even for the last pancake, which we don't have to flip at all, we'll just flip it twice just to be safe. Other than the very last pancake, which obviously we don't flip at all. So that's why it's n minus 1 and not n. But you could also just say 2n, same thing. Everyone see where that's coming from. Roughly 2 flips per pancake. That's how you can think of it. But the key part is setting up the recurrence. So this is called a recurrence. It's just a function whose value depends on the function value at previous steps. So you should have seen this before in 240. Won't go super deep into it. But I will tell you how to solve these later on in the lecture. Okay? So one question is, what does the worst case look like? What stack of pancakes should I give you that will get the worst possible number of flips? It's okay if you don't have like an exact answer, but if you have like a rough feeling, that works too. Yes?
Probably it's just completely upside down.
So completely upside down can be solved in 1 flip.
Oh.
But good suggestion. Yes. That's roughly the idea. Yep. Yeah, so alternating is the answer. So why? Let's think of this. So we have, let's say, small pancake, then the biggest, then another small one, even smaller, pretty big, something like this. So to move the biggest to the bottom, we definitely need 2 flips. 2 flips. And now after we've done that, look at the substack. The substack has a similar structure. So where the biggest will also need 2 flips. So basically by alternating between big and small, you will always force the algorithm to take 2 flips. That's the idea. Now to get the exact instance that's the worst, it's actually kind of tricky because you have to think of the future flips. So the specific ordering is important, but the idea is they're going to alternate. And that's going to get you close to that 2n-1 running time. Okay? So any questions on this? And I'll say briefly, if the pancakes were burnt and you wanted all the burnt sides down, how could you tweak this? Just need one extra step. Yeah, so you get the biggest to the top. If the burnt side's facing up, just flip the whole stack because now the burnt face is down. But if the burnt face is facing down, you need one extra flip, just the top pancake, and then do it. So you just add one extra step each time in the worst case. So you can extend this. Can extend to burnt pancakes. And you get like 3n. So just to illustrate, this kind of approach is still similar for different types of problems. You just have to think about how you tweak the initial step of simplifying the problem. So any questions on pancakes before we go to actual computer science stuff? Yes?
Is this the optimal pancake flipping algorithm?
It is. Surprisingly, it is optimal. It is optimal for the non-burnt version. For the burnt version, I don't think it is. I think there's a different... I don't even know if the optimal is known, but you can show it the ones we have are not optimal. There's specific stacks where you could do better. Yeah. And I should say, it's optimal for worst case pancakes. So even the original algorithm, for some instances, you could not flip sometimes and it'll be better. But for the specific worst case example, it will be optimal. In general, algorithms usually aren't instance optimal, where it's optimal for each individual instance. But they can be optimal asymptotically in the worst case. Other questions? Yes?
Something weird, but what if it was a constraint on the amount? That, in this case, it is all of them, but let's say you can only flip 3 at a time. How would that complicate things?
So that would just increase the number of flips you need. So basically, I'm going to think of this as an array problem because physically you can't really do flips. But if you had an array and you wanted to sort the array where you could move only within a sub-block of size 3, the main difference is you're just going to need more flips because you can simulate a whole flip by just slowly moving your window and just carrying things over. So you could do a similar idea, but now it's just going to take way longer. That's what it'll look like. Anything else before we go to sorting non-pancakes? Okay. So these are the key ideas. So that's why I took 30 minutes on pancakes, because the same ideas are going to carry over to even the most complicated examples. Like merge sort, okay. So everyone probably has seen merge sort before, I would assume. So the goal here is we want to sort an array. I mean, pretty basic. It's not as fun as sorting pancakes, but it's still useful, still important. Or you could just think of sorting a bunch of objects on a table. Really doesn't matter, that's an array. And how are we going to do this recursively? Well, as you can see there, you're going to take your array of items. So here, think of your array of items is just a sentence, and the elements of the array are the letters. So that's our input. We're going to break the input into two halves, the left half and the right half. That's the divide step. And now we're going to sort each half individually. The recursion fairy takes care of this. And then we're going to merge the two sorted subarrays. So step 1 and 2 are pretty simple. You cut your list of items in half. You tell recursion fairy to sort both sides. But just because you sorted both sides doesn't mean the whole thing is sorted. So the idea here is merging two sorted subarrays. So sorting a list where two sides are sorted is easier than just sorting the whole list. That's the hope, at least. So this is the key step, is the merge procedure. So I'm going to tell you how the merge procedure works, but are there any questions with the step 1 and 2 part? Yes?
Sorry, I was just thinking like after like the step recursive, right? Shouldn't there be like additional steps compared to the initials of each array?
So that's what's going to happen in the merge.
Okay.
The merge is going to do all that. So step 1 and 2 is just literally sorting two halves of the list. That's it. And assuming we have the two halves sorted, step 3 is going to now combine them into sorting the whole thing. Okay, so how do we do the merge? That's the key thing. How to merge. And you might have seen this before, but I'll just kind of draw it out. So this is a sorted array. This is a sorted array. This is a horrible example. Let's make this bigger. Okay, so we have these two arrays that are sorted. We get that for free thanks to the recursion fairy. So now how do we create these or merge these to create a bigger total sorted array? And the idea is, okay, so let's just look at the first entries. Because these are sorted, we know that the smallest thing here, so let me use green. So we know that smallest element, that is the smallest element. So because they're sorted, we know this is the smallest. 1 is smallest in the array A. So this is A, this is B. And similarly, because B is sorted, we know 6 is the smallest. Okay? So what's the smallest element in the total array? Well, it can't be better than the first element of A and the first element of B, because they're sorted, right? That would mean there's something like -2 over there. But because they're sorted, -2 can't be there. So we know the only possible choices for this element, the first thing in the complete array, is 1 and 6. Does that make sense? So we're using the property that these subarrays are sorted to efficiently figure out how to sort the other array. So we throw in 1 there because 1's smaller than 6. And now we move to compare 8 and 8, or 8 and 6. Now we do this process again. So we know the only options are 8 and 6. 6 is smaller, so we put 6 next. So this is done. We move again. Now we compare 8 and 8. Obviously, it doesn't matter, they're tied. So let's just move again. And so you see the idea here. It's actually recursive. We're also doing recursion here. We figure out which element goes next in the array, and then we recursively do the process on these two smaller arrays. Actually, let me do purple. So we're recursing. Everyone see that? So we pick off one element from each array, put it in the final output, and then recursively repeat the process. So I'm kind of emphasizing this a lot just because you've probably seen this as a loop, because it is a loop, but really this is also recursion. Loops are just recursive algorithms. So here's the full pseudocode. The merge sort algorithm just literally splits the array in half and sorts both, and then calls merge. So nothing complicated there. The merge algorithm, on the other hand, it's just doing the process I just described to you pictorially. So it's going through each subarray one by one and looking at which one's the smaller. Whichever one's smaller goes into our output array B, and then we move the pointer to the next one. So the pseudocode's just exactly capturing that process with the pointers moving. But you could also think of it as a recursive algorithm. Now the only difference between this and what I showed before is there's base cases built in. So these two are base cases. What do these say? So if j is greater than n, that's saying that we have no more elements in the right array. So the right side array ran out of elements. Well, then obviously, we are only going to take things from the left array because there's not even anything to compare in the right array. And similarly, if I is greater than m, that's saying we're outside of the left array, and so we have to just take elements from the right. Okay? So I'm going a little fast just because I'm assuming you've seen merge sort before, so I'm just kind of emphasizing the recursive parts. So any questions about the merge sort algorithm? Before we prove it by induction. Twice. Yes.
Is there an advanced algorithm for the mark part? I just wonder.
Is there like a better way to merge?
Because you just compare one by one.
Asymptotically, no. If you just mean like for a specific instance, yeah, there's always a better algorithm. But in terms of big O notation, no, you can't actually beat this. You could only improve the constants. Yes?
So I've usually seen the merge stuff represented as like two pointers running along the little arrays and then they're shuffling the things in. With, oh, maybe it does have recursion because it goes to the other cases. But I've not seen it individually with the recursion in there. Did you do that intentionally? And if so, why?
So yes and no. So every loop is recursive. So in a sense, it's intentional because everything's recursive. But I don't believe the algorithm was purposely modified. I think Jeff just picked the easiest merge sort to describe. I don't think he intended it to be like the one best conducive to recursion. But maybe he did. He's pretty smart. That's all I can say on that. But yeah, you can think of any loop as really being recursive because you do something at the current iteration and then recursively take care of the rest for the rest of the iterations. It's the same thing. It's just more efficient to make it a loop if possible in code. So any other questions on the actual description of the algorithm. Okay? That's merge sort. So now we need to prove it correct, of course. We need correctness. It's kind of useless if we have an algorithm that doesn't work. It'd be really sad if you had a constant time algorithm that just didn't sort your array. You would get fired, I promise. So we need to make sure it works. So here's a lemma. There's two things we need to prove. We need to prove merge works, and we need to prove merge sort works if merge works. So remember, when you do reductions, you're treating the other problem as a black box. So if you're someone who's writing the merge sort algorithm, you don't care how merge is implemented. You need to assume it's working. You don't want to take someone else's merge code from the internet and like scan through it and make sure it works. You might as well just write your own merge code then. So it's critical that you trust the merge algorithm. And so assuming merge works, then merge sort also works. So the correctness of merge sort cannot depend on the correctness of the merge algorithm. You're just going to assume merge works. Just one thing I want to emphasize there. Okay? So that's how we're going to prove this. And then obviously, you know, this is, if this is true and the if statement is true, then the conclusion is true. So this would, together, implies merge sort works. It's like modus ponens or whatever, if anyone cares. Okay. So the first step is to prove merge works. This is actually the hard step too. So we want to prove merge correctly merges these two subarrays. These are the input arrays right here. M is the middle point, so you can think of these are roughly the same size. And the key thing here is we're going to assume those subarrays are sorted, and that's critical. The merge algorithm will not work if the two input arrays are not sorted. That's a critical assumption. You always want to be very clear with the assumptions you're making on your methods. Okay? So what's the proof? This is not the proof. This is just the setup. So we take our array A, we split it into two pieces that are sorted. Now what we're actually going to prove is that by induction on K, so let K be a number, 1 to n. We want to show that any step in the process, B, K through n, is sorted. And we're going to start with AI through J, or AI through M, B, sorry, this is AJ through N. So we're doing this backwards, so I just want to emphasize that. So no, come back. So let me tell you what this number k is. So k intuitively is the current iteration in the loop. That's what this number is, k from 1 to n. And n minus k plus 1, this is the number of elements not yet sorted after the kth iteration. Okay, so we're proving this by induction on this, the number of things left to be sorted. So whenever you're doing induction proofs, especially on loops, it's a little unclear, like what are you inducting on? you want to have some measure of progress. And here the measure of progress is n minus k plus 1. It's telling us how close we are to being done. So when k is equal to n, there's one element left to be merged. And we can merge one element without doing anything, right? Or you could even let k equal n plus 1, in which case it's 0. There's nothing left. So when k equals n plus 1, n minus k plus 1 is 0. So nothing left to be merged. Okay, so that's our measure of progress. At each step in the loop, we've reduced the number of things that need to be merged by 1. And this is what we're going to induct on. So we're going to prove this by induction. On n minus k plus 1. So let's look at the induction proof. So what's happening here? Well, we have our subarrays that we're merging. And so what we really want to prove is that b of k is equal to the min of a I through m and a j through n. What does this mean? We've effectively chosen bk to be the smallest element in these two sublists. So remember, this is I through m and j through m. It's not the full thing because we're assuming we're in the middle of the process right now. So we've already done like 20 iterations. So now the first element in the left array is moved over, and the first element in the right array has also moved over somewhere. Okay? So this is what we want to show. That's the key thing. We're correctly doing the merge for the current step. So now we're going to use the definition of the algorithm. So let's go first to the base cases. So if j is greater than n, we've fallen off the right array. So if we've fallen off the right array, our only option for the minimal element is the smallest thing in the left array. So we know that a of I is equal to the min. Union the empty set. So the right array is empty, it's nothing, and we know by definition by assumption, we're assuming that AI is the smallest element of AI through M because it's sorted. So this is by assumption because A1 through M is sorted. Are we clear on that? I'm going to have to make another page. I tried so hard. Cool. We have more room now. Okay. So if we have nothing left in the right array, we just take the first element of the left array. Yes?
Did you mean to say the subset of A from 1 to M in that last part there? Because the assumption otherwise is.
So if A1 through M is sorted, AI through M is also sorted. So pictorially, if this whole thing is sorted, then this part's also sorted. Make sense? If this part had like a 7 and a 6, then the whole thing also is unsorted. Okay, yes.
Why did you take the UD with the empty set?
Because AJ through N is empty.
Oh, okay.
Yeah. So remember, we want the A of these two things, the min of these two. I just threw a union instead of a comma. Okay. So if I is greater than m, this is basically the same thing. We've fallen off the left array. So again, AJ is the min. Okay. Now the reason why our algorithm is correct is because we know these are the mins, and by definition of the algorithm, def of merge, we set BK to be AI in this case, and we set BK to be AJ in this case. Okay? So just to refresh your memory, here's the merge algorithm. That's exactly what happens. That's the wrong part. Here. So if I is greater than m, BK is AJ. If J is greater than, BK is AI. That's exactly what merge does, and so these are correct. Clear? I'm not getting enough enthusiastic nods. This is not clear. Please ask a question if it's not clear. Okay, so the next case is when they're both not empty. So the other case is, they're both not empty. So by definition of our algorithm, we just pick the minimum. To be BK. And again, it's the same idea. So the minimum of AI and AJ is going to be the minimum of all of them. I keep saying B. Why is that? Again, it's because they're sorted. We know the smallest between the two initial elements is going to be the smallest of the two arrays overall. So this, again, by assumption, that the left and right arrays are sorted. Okay? So, so we've shown that for one step, what we do is correct. We've correctly merged BK. So we know at iteration k, technically it's iteration n minus k. BK is correct. Then the induction hypothesis implies all the rest are correct. And because we're in the middle of the process, we're also kind of assuming the rest were correct. Or we've already done B1 through K. There's also this assumption we've already So we have that B1 through K is correct by the argument above. Then the rest is correctly merged by the inductive hypothesis or by the recursion fairy. And so if we correctly merged the first half and the second half of the array, I mean, it's not really the half, but some arbitrary breakdown of the arrays, this implies the whole be 1 through n correctly merged. Other than the base case, so of course the base case is when you're not even in the loop. So if you're outside the loop, that means k is greater than n. That means your arrays are empty, there's nothing to do. Okay? So let's just, as a refresher, let's look through it again. So we proved this by induction on the number of elements left to be sorted in the merge, or left to be merged, to be precise. So if there's nothing left to be merged, that's this base case here. If there's nothing left to be merged, well, we correctly do nothing. Free base case. On the other hand, if there are some elements left to be merged, we've shown that the current iteration correctly picks the minimal element to put in BK. So that's these 3 cases. We've shown in each case BK is the minimal element between the 2 arrays. And then by the induction hypothesis, the rest of the array will be correctly merged. So overall, the entire thing is correctly merged. That's the full proof of the merge algorithm, okay? So that's the hard part. Any questions on that proof? Yes?
So we can assume that the arrays are properly sorted.
Yes, so that's an assumption in the actual lemma.
So for the first 2, like if down on the production process, yeah. So for the first 2 of those, since we know that I to n is sorted, could we just say that if j is bigger than n, it's just ai?
Yeah. That's basically what I did, just with more words. Yeah, what you said in English is exactly what I'm writing in symbols.
Also, like if we just like skip through like the n and like combining process, would that still be like correct deduction?
So if you didn't do this like in a loop, but just said BK is the rest of the left side instead of 1 by 1.
No, like if we skip like the min, ai, and merged with nothing, that entire portion, since ai is just
Okay. Cool. Any other questions with the proof? Yes.
so the 0 with a slash means like those empty or
Empty set, or an empty array. So it's the array with no elements. I'm going to use that in general, like empty graph, empty whatever. Anytime something has just nothing, we use that notation. Yes?
If we know that we've fallen off the right array, do we just say that AI is equal to the minimum of AI through n? Like, we don't have to include that in step.
I personally included it just to make it clear where that's coming from. But yeah, they're equivalent.
Like, if this was like a homework problem, can I just say immediately that we know that it's equal to the left?
Yeah, absolutely, for sure. I'm going in more detail here just so you're comfortable. Like, I don't want to just say something that actually has to be unpacked. I want you to see all the steps. But absolutely, it's up to your judgment. If you think it's clear just to say that, you should. And I would say in this case you should do that. That would be more efficient. Other questions? We're going to see more proof examples, so if it's still a little fuzzy, we'll fix that. So this one's easy. So how do we prove merge sort's correct now that we know merge is correct? We don't even have to write a proof. Let's just prove it here. So this is correct by the recursion fairy, i.e. the induction hypothesis. This is correct by the recursion fairy, i.e. the induction hypothesis. So by the induction hypothesis, we've correctly merged, or we've correctly sorted both halves of the array. Then by our lemma, we know that merge will correctly merge two sorted arrays. And so by the lemma, merge correctly sorts entire array. Done. Is that part clear? So this part's great because the recursion fairy does everything for us, and then our merge friend does the rest for us. You have done literally nothing. You've handed off problems to 3 friends and they did all the work for you. That's how you want to think of it. You don't have to worry about the fact that your merge friend is actually you. It's not your problem. Pretend it's future you's problem, okay? So because the way we've abstracted this into, the recursion fairy and a reduction to the merge problem, using these reductions has simplified our lives in the present. We don't really have to do much work. We get these guarantees for free. Any questions on that? Yes? The base case, if n equals 1, we do nothing. A single element is already sorted. There's nothing to compare it to. Good question. Does that answer your question? Cool. So if n is greater than 1, we're in that. So the base case is when n is 1 or smaller. So to be precise, let me say if n is at most 1. Okay? Cool. So let's look at another sorting algorithm, quick sort. So the idea behind merge sort is you do all of the work after the recursion fairy. So the recursion fairy sorts the 2 subarrays, and then you do some stuff. So for merge, all your work is after the recursion fairy. So quick sort's just the reverse of that. So you're going to do all of your work at the beginning and then just have recursion fairy end the process for you. So the last 2 things will be recursion fairy in this algorithm. So how does quick sort work? Well, you're going to pick a pivot element in the array. So here the pivot element is p. And now you're going to move everything smaller than p to the left, everything larger than p to the right, and put p wherever it belongs. So essentially, you're going to sort p. You sort a single element at a time. So now after you do this, these should all be smaller than p, smaller than p. These are all larger than p. So p is in the correct spot. Okay? So if we know everything in the left is smaller than p, and if we recursively sort the left side, and if we also recursively sort the right side, then the whole thing's going to be sorted. And you don't have to do anything else at the end, because P is already in its correct position. So if everything's sorted on the left, you have P. Everything's sorted on the right, you're done. Any questions on, yes?
So how do we choose the pivot point?
That's a great question.
Yes, it's like it can determine like the steps we're going to take subsequently.
So there's a gazillion ways to choose it. Most people choose AN, the last element. This is just for simplicity, but there's a lot of better choices. So you could do random, pick a pivot at random. I think that's actually the best. So pick at random is probably the best. There's also more complicated ones that I'll talk about later, but those are some options. So it sounds like already you're thinking about the worst case. Depending on that A, this running time might not be so hot. And I should mention, so for merge sort, I didn't really talk about the running time because we're going to talk about it later. But if anyone was curious, it's O of n log n. And I'll show you how to derive that in a bit. Okay, so here's the quick sort algorithm, and its full glory. We choose our pivot elements. We partition, which means we moved everything smaller than the pivot to the left, everything larger to the right of it. So you could think of this as you've put P in the middle. You're not literally doing that, but you could think of it like that. I saw. It's refreshing. So it's like putting P in the middle, and then you quick sort the left, quick sort the right. So of course, just like before, all the meat is in this algorithm, the partition algorithm. So what does it do? It does like the most obvious thing you could possibly do. It literally just loops through the array. So you move through the array, you check, is the current element I smaller than AN? So the first step, I should say, the pivot is going to be an AN, just because we put it there. So we directly put it there. So even if it wasn't literally AN, we've swapped it so that it's now at the end, just for convenience. So we're going to compare AI to AN. And we're also going to keep track of all the smaller things. So we also have 1 through L are all smaller than AN. So this is kind of the important part. We meant to use a highlighter. So we always keep track of this list of smaller things. And then if we find out that AI is bigger than AN, we don't do anything. If we find out that AI is smaller than AN, then we're going to do a swap. So in particular, let's think of I being over here. So overall, we have these two lists. These are all smaller than AN. These are all bigger than AN. And now we want to figure out what to do with I, which is over here. So what do we do with I? Well, the whole point of the algorithm is we want to maintain this structure. We want all the small things to be in the purple, and we want all the large things to be in the orange. So if I is bigger than AN, we do nothing, and it just is added to the orange by default. But if AI is smaller than AN, then we need to move it to the purple. So what do? We literally do this. Swap. So if we do a swap, that orange thing, which we know is bigger than AN, stays on the orange side. But now we've increased the purple subsection by 1. So now that one becomes purple, and this one becomes orange because we swapped those two. So at the end of that, we've still maintained our subdivision. We still have the colored blocks are correct. And so we keep doing this step by step, and at the very end, well, we'll have the correct purple and orange blocks. And then we can just slap P in the middle. So at the very end, we do this step right here, which literally just puts AN, which is the pivot, right here. So that's correctly sorted. So at the end, put pivot here. So you can see visually after the end of the process, you have everything less than AN, and then everything bigger than it, or the pivot, if you don't want to call it AN. So that's what's actually happening in this code. You're literally going one by one and deciding, should I move this into the purple region, or should I just extend the orange region by 1? Okay, so any questions on that? Clear? I think the colors helped. Normally when I look at this algorithm, it's very weird, but I like the colors. Yes?
So in the case when the first element is smaller than the pivot point, it would just swap itself, like, right? And then the L would increment up 1, but it would be the same.
I think, yeah, I think so. So let's look at this line. So what you're saying is the case when L equals I. So let's say I is 1. I is 1. And now L is 1 because we did L is 0 plus 1. So you just swap it with itself. That's correct. So this is just another example of you could actually optimize these algorithms to be better, but these are simplified versions for readability. So we're going to do a swap with itself, which really does nothing. It doesn't really horribly increase the runtime or anything, but that is something you could take out to make it run faster in practice that we've left in for readability to make it simple and flow well. And I would generally encourage you to do that in algorithms as well, is when you're describing an algorithm, write the simplest and easiest algorithm you can first and worry about optimizing stuff later. It's much easier to start easy and go to hard instead of starting hard and getting really confused with all the details. And then you've kind of poisoned your mind and it's hard to think straight after that. Yep.
Where do you put the pink element in the middle if you swap with the current element?
Do you mean at the end of the process with the pivot?
When you swap to I, then you advance I, how do you know that that one belongs there?
So by definition, if we did a swap, so remember, so this element right here was orange before. So we know it's larger than the pivot.
Oh, okay.
We basically said instead of making it orange, make it purple, and then we just moved the orange over. So we extend both sides by 1. Any other questions? Overall, this algorithm is just, you have purple and orange blobs, and you just move the blobs over time. That's it. Okay. So how do we prove this thing correct? So let's first prove quicksort correct. How do we prove quicksort correct? Well, again, we have to assume partitions correct. So if we assume partitions correct, what the algorithm does is the following. These are all smaller than p. This is larger than p. This is p. And then by the induction hypothesis, this is sorted. By the induction hypothesis, this is sorted. And so the whole thing is sorted because you sorted all the big elements, kept them over there. So in particular, what could go wrong? What if you had like a 5 here and a 10 here? Why can't that happen? Because of the definition of partition. So by definition of partition, and let's say p is 7, anything smaller than p had to be in the left side. So if this ever happened, partition would have swapped them. Okay? So, whenever something's vague, just think of what could go wrong, and then you'll see it can't go wrong. So if, for some reason, even though the recursion fairy is doing the right thing, the overall thing still didn't work, it was still not sorted, that implies we must have had an inversion. An inversion, it just means that you have something bigger in front of something smaller. So if we had such an inversion, that implies partition didn't work the way it's specified. But we're assuming partition does work. And so because we have that assumption and we have the induction hypotheses, overall we have the array sorted. And then again, the base case, it's kind of an afterthought, but you should write it. If n is at most 1, it's already sorted. Proof complete. Okay? So how do we prove partitions correct? Again, it's a little more complicated. It's gone. I had a proof for it, but it's gone. So let me tell you what the proof looked like. So again, it's kind of like an induction proof. There's 2 loop invariants. The loop invariants say the purple block are things smaller than p. The orange block are things larger than p. And so as you go along, you're maintaining that property. So let's say at the current step, we were at I and we decided to do a swap. So then after this step, we know that the purple block is still correct and the orange block are still correct because of these conditions here. These conditions are designed to make sure that's true, that things smaller are in the purple and things larger are in the orange. So we know just by directly analyzing it that will be true for a single step. And then, there's some number of elements not yet partitioned. By the induction hypothesis, those will be partitioned. So the whole idea here is you want to show that the remainder of the array, ai through n minus 1, is partitioned correctly. And to prove that, you show it directly that ai is partitioned correctly. And then, ai plus 1 to n minus 1, well, that's a smaller array, right? We've taken off one element we have to consider, so now we can apply the induction hypothesis to that. So you show for any step in the algorithm, one iteration is correct, and then by induction, the rest of the iterations are correct. And so at the end, you'll have the purple and orange blocks exactly capture what we said they do. Make sense? And you want to kind of get these induction proofs to be second nature. In my opinion, the hardest part is figuring out the measure of progress. Once you have a clear process that has some measure of progress decreasing, the induction proof's pretty quick, because you just say, okay, this thing's decreasing, one iteration works, then I have a smaller thing, induction. So the hard part is really figuring out your measure of progress. So let me just say that. Hard part, finding a measure of progress. After that, it's really just show one iteration works. And then induction hypothesis on the rest of your structure. It doesn't have to be array, it could be whatever. It just has to have smaller progress or whatever your measure of progress is. It's pretty much the overall schematic. And there's one little point that I kind of mentioned, but I'm skipping over, is remember we're starting at some I in the middle of the process. So I'm assuming that the previous iterations were also correct. So you're assuming the previous iterations are correct, and you're assuming the later iterations are correct, but you're doing it in a different way. So for the early iterations, you're assuming it's correct, just literally by assumption in the theorem. The rest you're assuming correct by the induction hypothesis. So there's two kind of different assumptions there that are played out differently. But usually you don't really care about the previous iterations are correct thing because it's kind of obvious. But I just want to mention it for technical reasons. So Jeff talks about this a little bit in the notes, but just wanted you to be aware of it in case you see that and you're like, what's going on? Okay. So any questions about quicksort? Okay, so we've seen 3 examples now of using recursion to do various sorting tasks. And so let's just take a second to kind of summarize what we've done so far. So you've probably heard this before, this idea of divide and conquer. And there's 3 steps. We divide the problem into smaller instances of the same problem. Now remember, for reductions, it doesn't have to be the same problem. So for a general reduction, it can be a different problem. It doesn't have to be the same. But for divide and conquer and recursion type reductions, it has to be exactly the same problem. So our recursion fairy is kind of limited. She's not all powerful. She can't solve anything, but she can solve the exact same problem you want to solve. So this is important because if you say want to solve, so for the sorting example, let's say your algorithm requires you to solve, you're sorting 1/2, but you're sorting it in decreasing order now. If you tried to do that, this would fail, because it's not the exact same problem you're trying to solve. So it's really important that you check that the problem you're reducing to, or when you're recursing, the input is exactly the input to the original problem, other than the size is smaller. Okay? So we do the divide, then we delegate each smaller instance to the recursion fairy. That's just saying recurse on each of those smaller pieces. And then the end part, this is the important part where we combine those solutions together. So for merge sort, we do a merge process, which is kind of complicated to build the final array. For quick sort, we do nothing, right? So at this point, we're already done. We have nothing to combine. All the work went into dividing it properly. So let me write that. So for quick sort, this is the hard part. For merge sort, this is hard. And for pancake sorting, it's more of the divide part. because you move the pancake to the bottom first, and then you ask the recursion fairy for help. Okay? And then, of course, the base case is an afterthought again, but it just says if the size of your instance is small, so maybe your array's like size 100, then you can just brute force, do whatever, it doesn't matter. So for purposes of this class, that's any constant. So no dependency on n. This includes things like this. So that number I just wrote is probably the biggest number of all time. Like, this number is gargantuan. You would never see this in real life. But for us, that's a constant. You can use your base case to solve that. It doesn't matter. As long as it doesn't grow with n, that can be your base case. So pick any number, and for arrays of that size or smaller, do brute force. What is brute force? It could be like a bubble sort, it doesn't matter. You can just assume you can brute force stuff. You don't have to specify exactly how to do it. Realistically, it's probably something smaller like 2. So like arrays of size 2, you can sort it just by doing a single swap if you need to. But any number without an n in it counts as a constant. So that can be your base case. Okay? So this is the general framework. This is all describing the algorithm or deriving the algorithm. Now, of course, with any algorithm, you need to prove it's correct. For these types of algorithms, it's almost always induction. And you need to analyze its runtime. Usually you use a recurrence, like the t of n depends on t of n minus 1 type thing. And in particular, we're going to talk about this part next. We're going to focus on this. So any questions about the rest of this? Kind of the overall strategy and the proof strategy. Yes?
Do you want to elaborate on what is
N is the input size.
input size has to be an array, cannot just be one?
It can be anything. So for a graph, the input size is like the number of nodes. That's n. For a matrix, it's like n squared, the number of entries. Yeah, depends on the context, but we just say n to mean problem size.
So what is the difference between n and a constant?
N is something that can grow. So by definition, a constant's a fixed size that doesn't change. N can change over time. So you can think of there's more people on the roads. Whereas, you could have a fixed number of drivers on the roads. That never changes ever. The whole point of this is over time, there's more people. The problem sizes we have to solve get bigger. And so we need our algorithms to be fast with respect to n, the number of things. Okay? Any questions? Like I said, ideally, when you're deriving the algorithm, if you're thinking recursively and you're thinking about the recursion fairy, you get the proof of correctness for free. So if you do that, kill 2 birds with 1 stone. It's much faster. The analysis usually is pretty easy too, and that's what we're going to talk about next. Wow. That's what I expect to see on your homeworks. Okay, so how do we solve recurrences? So what exactly is a recurrence? We're solving, or we're looking at a recursive algorithm. And let's say this recursive algorithm spawns R children. So there's R children, or there's R recursive calls it makes. And it does, each child is of size n over k. And we also need to specify the runtime outside and does f of n work outside recursion. So what are each of these? Let's think of pancake sorting. For pancake sorting, the number of children is 1. You only have one recursive call. The size is n minus 1. Here, I'm going to make sure it's closer to an even split, so it's not exactly the same. F of n, the number of work outside recursion, would be 2. That's the number of flips we have to do, ignoring the recursion calls. For merge sort, we have 2 children. Child size is n over 2, because we have roughly arrays of half the size. And the amount of work we do outside the recursion is O of n, because we have a loop of size n. Each iteration, you do a constant amount of work. Okay? And so the running time, T of n, looks like this. R times F of n over K. Oh, not F. Not F. It's T. Plus F of n. So that's our running time. And we want to get an asymptotic bound. So we want something like T of n is O of n log n, something like that. That's what we want. So the method we're going to do this is called recursion trees. It's a really simple technique. You draw a tree. Oh, here's my proof of partition. Wow. Okay. So recursion trees, the idea is you're going to quantify how much work you do at each level of the recursion. So at the top level of the recursion, you do f of n work outside of the recursion. You spawn r children. And each child has size n over c, not k. Okay, got the number wrong. It's k. Why? There we go. So you do f of n work at the top level. Then you spawn r children. Each child is of size n over c. And so if you sum them all up, at this level, you're going to get r times f of n over c, because you have r children, each doing f of n over c work. And then you repeat this process. You get even more children, but they're of much smaller size, and then you can sum up all the work they do, and so on. So you're breaking down the work done by the recursion level by level in the recursive tree, basically. And then you sum it all up. You're going to sum all of this up, and that will be your total running time. Okay? So that's basically it. Now what's cool is this method will give you some general guarantees. So decreasing means the series decreases exponentially. So this is something like, let's say this was 1, 1/2, 1/4, etc. So if your running time grew like that, or I guess to be more precise, it'd be more like n over 2, n over 4, etc. So if your running times grow like that down the tree, that means it's in the decreasing case. Similarly, it's increasing if it's the opposite. So you could have n (2n, 4n), and it just keeps doubling. So in general, it's like 2 to the ln. That would be in the increasing case. And then you have the equal case, where you just have n, just n's forever. And depending on which case you're in, you can get an immediate bound on your running time. So for the decreasing case, the bound is going to be O of f of n. This says that the work you do at the very top of the tree is the most dominant. So you're doing all your work at the beginning, and everything else is pretty small comparatively. So overall, you're just doing the top level work. For the increasing case, it's the opposite. You can ignore everything else except the leaves, the bottom of the tree. And the bottom of the tree dominates your total running time. In the equal case, you just get this nice equal thing, which is f of n log n. It's really pretty. This is the goal. If you can get an equal thing, that's the easiest to analyze. So these are just some cool, this is called the master theorem. You can see more of it in the notes. Super useful for like homeworks and stuff. But you don't even need to use this if you don't want to. You can just like logic it and figure stuff out. So let's do that. Let's look at merge sort. So merge sort, we're doing n work to do the merge. It's technically O of n, but when you're doing these recursion tree ideas, just ignore constants. They don't matter. Then you're going to have two children of size n over 2. Again, they might not be exactly n over 2. If n's not even, it could be like, n over 2 minus 1, n over 2 plus 1. But it really doesn't matter, so you can just make it as simple as possible. It's n over 4, n over 4. Usually 2 layers is enough. Dot, dot, dot. So at the top level, we're going to do roughly n work. So merge is linear time, and the size is n. Now on the second level, each of these does n over 2 work, but there's 2 of them. So you get 2 times n over 2, which is n. Okay. Similarly, we have 4 times n over 4, which is n. So this is the equal case of the master theorem. But even if you didn't know the master theorem, we can still figure out the total running time just by summing it up. So let's just do that. So let's say there's L total levels in the tree. Then the running time, T of n, is the sum from I equals 0 to L of n, which is just roughly n times L. So let me just make this a 1 to make it easier. It's just n times L. So what's L? L is when we hit the base case. Okay. So for merge sort, we hit the base case when the size of the array is smaller than 1. So roughly, if we made like an equation for that, we have n divided by 2 to the k, or actually we can just call it L, equals 1. Or to be really precise, it has to be at most 1. So we keep dividing our input size by 2, L times, so n over 2, n over 4, and it's going to keep dropping by a factor of 2 each time. And so we hit our base case when this equation happens. Make sense? So when we halved it enough times to where we have 1 element left in the array. And so we can just solve this with logs, right? So you can rearrange this to be n is at most to the L, and then just take log base 2 of both sides. You get log base 2 of n. L is at least that. But we can make these equalities. So L is log base 2 of n, and so our running time is going to be n log base 2 of n. Now remember, this is like a simplification. We ignored constants and stuff. So really, this is big O. And because it's big O, log factors, like the sub 2 in the log, doesn't matter. Log base 2, log base 100, they're all roughly the same up to a constant. So we can also remove that and just get log n. That's unfortunate. Okay. Make sense? Yes.
The n times, oh, isn't this was like n times I, because that is n times as I iterates up until or am I just driven over?
So I got rid of the I because I'm summing n L times. So it's n plus n plus n L times, which is just n times L. So this is n plus n. So here there's no like n to the I or anything. I actually plays no role in the recurrence. So here's an example of using the recursion tree method for a balanced tree. And this is usually the case, it's not, this is pretty common actually for most examples. Any questions? So now we're going to look at some harder ones. So this one's for quicksort. Technically, this one also works for pancake sort and pancake. So what are these trees? So let's think about the runtime for quicksort. So the nice thing about merge sort is we have this recurrence T of n is 2t of n over 2 plus n. That's really the recurrence that we ended up solving using this method. That's what the tree corresponds to, is that recurrence. Okay? Now for quicksort, it's a little more complicated because depending on the pivot you choose, that will affect the number of recursion calls you have. So the one on the left here is like a good case. So let's say our recurrence was t of n is t of n over 3 plus t of 2n over 3 plus n. So partition and merge both take n time. They're pretty much equivalent. But here, you don't have a balanced split. It's not 1/2, 1/2, it's 1/3, 2/3. And that could happen if you get a bunch of bad pivots. Actually, in this case, these are actually good pivots. The one on the right's even worse. So what's this one on the right? This is t of n minus 1 plus n. So that's what would happen if your pivot's always the last element in your array. Basically, you always get the left side of the partition has size n minus 1. Then you have the pivot, and then you have empty. So if everything's already on the left of your pivot, you kind of have to solve the entire problem. You're not really getting a lot of savings by subdividing the problem. And that's what the recursion tree would look like. So if your pivot is always really bad, you would get that. This is the worst case too. So this is the actual runtime of quicksort because we always think about worst case. This thing on the left, that might happen, but we can't guarantee it. So this isn't the worst case complexity, but just, for a specific, if you're lucky, you'll get this. In the very best case, we get exactly the merge sort guarantee. And this happens if the pivot is always the median, which is like the middle element of the array. So if you take quicksort and you add a subroutine to compute medians, then you could get this recurrence. But it's very hard actually, and that's why I'm saving selection for a video. But you could do it. You can modify quicksort to do that. But base vanilla quicksort gives you this guarantee. This is the guarantee of quicksort. But we can still think about the left one, so let's do that first. So this does n work, n work, n work. So if we look at the first, how many layers, we're still getting n work like before. The difference is these two cases hit the base case at different rates. So different rate for base case. And so this tree is unbalanced. If you drew out the whole thing, it eventually looks like one side will go much deeper than the other. So this is the n over 3 side. So you're going to hit the bottom of this. If you divide by 3 each time, you're going to get to the bottom pretty quick. But if you only divide by 3 halves, then it's going to take you longer to get to the bottom of the tree. So the initial portion of the tree is roughly just like merge sort, but near the bottom it gets a little different. So how do you handle these types of trees? It's actually real easy. You just pretend the whole thing is long. So just extend the tree and pretend they're the same size. Again, this is like doing a worst case type of thing. Okay?
So you're just making the tree balance?
Basically, yeah. But what's cool is because they're both getting divided, even though this side is longer, it's not asymptotically longer. It's just a constant longer. So you get something like log base 3 for the left side, really small. This side's going to be log base 3 halves. It's a longer, it's bigger, but it's not way bigger. So since we're doing big O analysis, these two numbers don't matter anyway. And so overall, we're still going to get n log n. So even if the tree's unbalanced, as long as we still have these constants, we're good. The issue is here. We don't have a constant. We're not dividing by a constant amount each time. We're just subtracting by some. So we're making very little progress, essentially. So if we look at this tree, we do n work, n work, n work. It's still in the equal case. But now, what's the depth of this tree? If you're just subtracting 1 each time, the depth is, or the height of the tree is roughly n. So you're doing n times, so that's going to be O of n squared for the path tree. Okay? So this shows you kind of the difference overall to these two schemes. As long as you're getting a somewhat even split, it doesn't even have to be super even, but as long as you're making a significant amount of progress on one side, then you're still going to get the n log n. But if you're only reducing your problem size by 1 each time, you get a significantly slower running time. Okay? So these are some examples of recursion trees. I also uploaded on Canvas an entire document dedicated to recursion trees, so I hope that'll be enough to get you the idea. So any questions on recursion trees? Drawing a recursion tree is itself an algorithm. It's a step-by-step process to give you the runtime. Okay? So now we're going to do one more example, one that's not sorting. Any questions before we go to the last example? Nope? Okay. So what do we want to do? I want to calculate a to the n. That's it. That's all I want to do. Very simple. So I want to multiply a by itself n times. So what's the easiest way to do that? Literally compute a times a times a times a times a. You just have a for loop where you just multiply by a each time. Who thinks this is a correct algorithm? One person? 2 people? Who thinks it's not a correct algorithm? No one. Okay, so it is correct. Like, obviously it's correct. It's just doing the actual definition of what a to the n is. How do we prove it's correct? We don't. It's obvious. But you could do it by induction. So what's the induction proof? So the induction hypothesis, x is a to the n minus 1. So then x times a equals a times a to the n minus 1 equals a to the n. That's the induction proof. But it's slow. You need n multiplications. The goal is to do better than that. Can we get significantly fewer multiplications? Who thinks we can? Who thinks we can't? Any thoughts? Yes. You want to say square, don't you? Well, kind of the answer's on the page. So there's another way you can compute powers using a nice little recursive scheme. So what is a to the n? A to the n is 1 if n is 0. Otherwise, if n is even, then we can just take a to the power n over 2 and square that. Because the property of exponents says this would be a to n over 2, which is a to the n, which is a property of exponents. And the other case is when a is odd. Well, if we're just going to round down and then add an extra factor of a that's missed. Okay? So it's called the repeated squaring algorithm because we're just repeatedly, we start at a and we just keep squaring it until we basically hit that power we want. The only difference is depending on, n being odd or not, we might add an extra a or not. Okay? So we can do this recursively. It's called Pingala power, but you can just call it repeated squaring because that's what it's always been called. But Jeff likes history, so that's why it's called that. But really, it's just repeated squaring. So what's the algorithm? If n equals 1, we return a. It's nothing to do. If n equals 0, we return 1. Heh, he missed a base case. So there's also if n equals 0, return 1. That's another base case. Otherwise, we recursively compute. So recursively compute a to the power n over 2. That's recursive. Recursion fairy does this. If n is even, we just square it, multiply it by itself. Otherwise, we square it and add an extra a in there. Make sense, everybody? Cool. So that's the whole algorithm. So, correctness, why is this correct? Well, by induction, of course. Or you could just do it by properties of exponents, same thing. So the correctness proof just says, it's basically what I said before, x is a to the power of n over 2. That's the induction hypothesis. So we can effectively multiply a by itself many times, just not the full n times. Then x times x, well that's a n over 2 squared, which equals a to the n if n is even. And same idea for n odd. So hopefully you're getting really comfortable with these induction proofs now. You can throw them at anything. They're great. Okay? So we know it's correct, but is it really faster? Can it beat n multiplications? Any ideas? The only idea I want to hear is, look at a recursion tree. Yeah. So you could like think about it, be like, well, we're kind of using half as many multiplications each time because you don't have to do all of them. You're doing like a halving thing. But, you know, there's no reason to be clever. Just make a recursion tree. It always works. So, what do? We have one multiplication at the top level. Then we have two children. It's constant. Then we have two children, each of size roughly n over 2. So this is starting to look a lot like the merge sort recurrence. And half the time, that's the solution. You just say, oh, it's the merge sort recurrence, but with a tweak, and then you give the answer. So here you're doing 1 or 2, but you're doing it twice, right? Etc. But each time it's constant. So let me just say like 1 each. So overall, let's look at the depth of this tree. So how many times do we divide n by 2 until we get to our base case of 1? I mean, it's the same thing as merge sort. It's going to be log n. So there's log n total layers, and each time we're doing some amount of multiplications. And so overall, we're going to have constant work per level, log n levels. So it's going to take O of log n multiplications. Make sense? I'm hoping this example is just really like pretty simple. Now, what I do claim though is although this is simple, this has huge impacts overall. So in particular, this applies to matrices too. So if you want to find a to the n for a matrix, for example, the adjacency matrix of a graph, then the way you calculate the shortest path in a graph, one way to do it is by computing that. So if you compute a to the n, that gives you the shortest path in a graph. Shortest path in the graph. And so instead of doing n multiplications, doing log n is a huge saving. You're exponentially improving the time it takes to find the shortest path in a graph. So even though this one example is just about multiplying things, it's about multiplying anything. As long as you can multiply an object, you can still use this algorithm. It's not exclusive to numbers. So this works for any object that can be multiplied. Whatever that means. So really, we've created like a family of algorithms, an entire scheme that improves the workflow for hundreds of other problems. And that's important for most of these algorithms, is they can be applied to many objects. You want to think abstractly about them. Don't focus in on it being like an array. Think of it as being just a set of stuff. The exact specification is not so important for this class. These are general schemes that work on general problems. Okay, any questions about that? We're just about done. So this is an example in the notes. I'll just skip this because the lecture is basically over. But before I let you all go, is there any questions about anything? And also announcement, don't forget, the homework is due Thursday at midnight, 11:59 p.m. on Thursday, and discussions tomorrow, lecture Wednesday, basically everything will operate normally now this week and forward.
I know the recording like after class maybe like a few hours after.
What was that?
Like when the recording can be uploaded.
Yeah, I'll upload it as soon as it's processed.
Yeah.